Infinite impulse response is a property applying to many linear time-invariant systems. Common examples of linear time-invariant systems are most electronic and digital filters. Systems with this property are known as IR systems or IR filters, and are distinguished by having an impulse response which does not become exactly zero past a certain point, but continues indefinitely. This is in contrast to a finite impulse response in which the impulse response h does become exactly zero at times tt for some finite t, thus being of finite duration. In practice, the impulse response even of IR systems usually approaches zero, and can be neglected past a certain point. However, the physical systems which give rise to IR or FIR responses are dissimilar, and therein lies the importance of the distinction. For instance, analog electronic filters composed of resistors, capacitors, and/or inductors are generally IR filters. On the other hand, discrete-time filters based on a tap delay line employing no feedback are necessarily FIR filters. The capacitors in the analog filter have a memory, and their internal state never completely relaxes following an impulse. But in the latter case, after an impulse has reached the end of the tap delay line, the system has no further memory of that impulse, and has returned to its initial state. Its impulse response beyond that point is exactly zero. Although almost all analog electronic filters are IR, digital filters may be either IR or FIR. The presence of feedback in the topology of a discrete time filter generally creates an IR response. The Z-domain transfer function of an IR filter contains a non-trivial denominator, describing those feedback terms. The transfer function of an FIR filter, on the other hand, has only a numerator as expressed in the general form derived below. All of the coefficients are zero and the filter has no finite poles. The transfer functions pertaining to IR analog electronic filters have been extensively studied and optimized for their amplitude and phase characteristics. These continuous time filter functions are described in the Laplace domain. Desired solutions can be transferred to the case of discrete time filters whose transfer functions are expressed in the Z-domain, through the use of certain mathematical techniques such as the bilinear transform, impulse invariance, or Polyar zero matching method. This digital IR filters can be based on well-known solutions for analog filters such as the Chebyshev filter, Butterworth filter, and elliptic filter, inheriting the characteristics of those solutions. The transfer function allows one to judge whether or not a system is bounded input, bounded output stable. To be specific, the Bibo stability criterion requires that the ROC of the system includes the unit circle. For example, for a causal system, all poles of the transfer function have to have an absolute value smaller than 1. In other words, all poles must be located within a unit circle in the dashed plane. Clearly, if then the poles are not located at the origin of the dashed plane. This is in contrast to the FIR filter, where all poles are located at the origin, and is therefore always stable. IR filters are sometimes preferred over FIR filters, because an IR filter can achieve a much sharper transition region roll-off than an FIR filter of the same order. Where is the unit step function? It can be seen that is non-zero for all, thus an impulse response which continues infinitely. The main advantage digital IR filters have over FIR filters is their efficiency in implementation. In order to meet a specification in terms of passband, stopband, ripple, and/or roll-off, such a set of specifications can be accomplished with a lower-order IR filter than would be required for an FIR filter meeting the same requirements. If implemented in a signal processor, this implies a correspondingly fewer number of calculations per time step. The computational savings is often of a rather large factor.